Yes.
What is like the structure of the grid going to be like the actual, like how do you get like the normal and Sij from like your grid information?
How do I get that from the grid information? Yeah. Okay. That's a very good question. So let me actually demonstrate using one thing. How do I do that? So for example, in MATLAB there is a good PD toolbox. Okay. So the PD toolbox is useful for generating a mesh. For example, if I just draw a circle over here and I click mesh, I get a mesh, right? So that's MATLAB PD toolbox supports the kind of unstructured triangular mesh. And then after you generate a mesh, you can export the mesh, into this environment. So we can have, can see we have E and P and T. So P is going to be all the grid points. So for example, if you plot P1 and P2, you get all the points where we generated. The T, the triangle, the T's are 4 by the number of triangles. So we have 992 triangles. The fourth column is all ones. It's the number of, it's the domain index. So in this case, we only have one domain, so it's all one. We don't need to care about that. And the other 3 rows, 1, 2, 3, are integers corresponding to the index in the P array. Okay, so this, for example, gives you the length. So the length of the triangle size and the direction of the triangle size are going to give you the surface normals, right? So for example, so let me just walk you through this one. So for example, I coded up a function. It's pretty short function that extracts the edges from the P's and T's. So from the points and triangles. So if you run it, for example, if extract edges P and T, what I returned you is an array of 4 by 1520, and 1520 turns out to be the number of edges in the whole mesh, and the four rows are, the first 2 rows are indices corresponding to the array P. That means which 2 points are these edge connected. The 3 and 4th row are indices in the array T. That means which 2 triangles is this edge separating. Okay, so if you follow the unstructured mesh finite volume, then it's the 3rd and 4th row that identifies the corresponding I and J of that interface. But you can use the row 1 and row 2 to calculate what is the normal and the Sij. So for example, if you compute the distance, so let's say ds, the distance between these 2 points would be equal to P of column, which includes both x and y. So the first dimension is x and y, of E1 column minus P E2 column. That'll give us the distance, the vector that points from one point to the other point along the edge. So the length would be just equal to the square root of ds1 square, square plus ds2 square, right? So that'll give me the length of each interface, right? These numbers are similar. Okay, so the surface normals would be equal to ds of 2 and ds and minus of ds1 divided by s. I don't know if the division works. Okay, so I have to wrap mat s over 2 and 1. So that's right. So that'll give me the matrix dimension must agree. S is this by this. If I replicate it, is it wrap mat like that? Oh, yeah, it should be semicolon, yeah. So that'll give me the normals of all the interfaces, right? Does that make sense? So it's all from like geometric manipulations of the mesh. Any other questions?
So, the number of points is like 529. So the number of edges should be 529C2, right? Or something less than that first.
No, because every point can share many edges, right? So if you look at the unstructured mesh over here, so every point has 1, 2, 3, 4, 5, 6, 7, 8. I mean, did I count correctly? I mean, every point can have many edges, and every edge only have 2 points. So the number of edges is equal to the number of points times the average number of edges shared by a point divided by 2, which is the number of points shared by an edge. So if the number of edges shared by a point is greater than 4 on average, then the number of edges is going to be more than twice the number of points.
So it should be number of.
Well, there is a relationship between the number of edges and the number of triangles. So if you look at T, we have this many triangles and we have this many edges. Every triangle is shared by 3. Every triangle is shared by 3 edges, right? And every edge is shared by either 1 or 2 triangles, depending on if that edge lies on the boundary or in the interior. So there is a inequality constraining the number of edges and the number of triangles you can apply here. But I don't see any constraints in the number of points and number of edges. Okay, any other questions regarding to this mesh geometry finite volume business? Okay, we are all fine. You can do this in your project. Okay. All right. So let's now we are basically talking about how to apply finite volume on multiple dimensions on complex geometry, right? So you need to generate a mesh, and there are plenty of mesh generators out there. You can use, if you just want to generate a 2-dimensional mesh, MATLAB is a pretty good mesh generator. If you want to go to 3 dimensions, MATLAB doesn't really do that for you. And we have open source mesh generators like Gmesh and commercial mesh generators like Pointwise that can generate good meshes for us. Okay, So once we generate a mesh, we can compute these surface normals and surface sizes, and we use the same type of reconstruction schemes. We use the same type of finite volume schemes to compute a flux as a function of the volume averages on the two sides. And then by accumulating this flux over all the edges, we compute the time derivative, which we can apply to an ODE solver to solve the differential equation.